Hi, I'm Lance Avery.
I'm Shannon Golightly.
And I'm Kale Schrack, and this is our presentation on the failure of Intelsat K.
All right, so starting off with some background and definitions, Intelsat K was a geostationary communication satellite owned by SES World Skies and built by Lockheed Martin that provided cable TV broadcasts to the Atlantic Ocean region. Coronal holes are openings in the sun's magnetic field where streams of high-speed solar wind rush out of the solar atmosphere. Electrostatic discharge is the transfer of electrical charge between two bodies at different electrical potential, and momentum wheels are the satellite attitude control system that allows the satellite to turn against the force from the spin of the momentum wheels. So, what actually happened to Intelsat K? A series of coronal holes swept across the sun between January 13th and 19th, 1994. At that time, the only signs of unrest near Earth were high speed solar winds from those coronal holes. The NASA SAMPEX satellite detected signs of energetic electrons near GEO, with concentrations rising to maximum. And then Intelsat K experienced an electrostatic discharge caused by the geomagnetic storm. And these satellites don't have a way to unload excess accumulated charges, so the Intelsat K's momentum wheels failed. This caused the satellite to begin to wobble, producing fluctuations in antenna coverage and causing service outage. The backup momentum wheels fortunately kicked on shortly after the wobble started.
So, what would happen if there were no backup systems? The satellites Anik E1 and E2 were affected by the same storm that took out Intelsat K. Anik E1 lost its main reaction wheels, but was restored several hours later thanks to its redundant reaction wheels. But however, Anik E2 lost both its main and redundant reaction wheels. Anik E2 began to spin continuously before it was corrected 5 months later, thanks to the usage of its thrusters to begin to orient its antenna properly. However, this had the side effect of significantly lowering the satellite's lifespan as its station keeping fuel needed to be used for those thrusters. And if this was uncorrected, all of the satellites would have been just spinning uncontrollably and effectively becoming dead weights in outer space. So, could this have been prevented? A possible prevention would have been by including an anti static coating on the craft. This may have been able to prevent the discharge from occurring in the first place. Making sure that spacecraft is properly grounded, allowing any potential discharges to not impede the critical functions of the spacecraft, and possibly including Faraday cages on any major electrical components. However, with the exception of grounding the spacecrafts properly, these add significant costs in both the financial aspect and the mass aspect of a spacecraft, especially using Faraday cages.
Now, moving on to the theory development. Now, first, to understand how the geomagnetic storm interacted with the spacecraft, we need to understand how the charged particles interacted explicitly with the surface. Now, as you can see, equation 1 correlates to the first figure on the left-hand side, where you can see the electrons and ions interacting with the surface of the spacecraft. In this very specific scenario, we can see that the velocity of the electrons and the velocity of the ions are both significantly faster than the velocity of the spacecraft at GEO, which increases the intensity of the ions. We can also see that the temperature of the electrons and ions are significantly higher at 10 to the 7th power Kelvin than, say, at a satellite at LEO orbit. Now, moving on to the failure analysis, uh, we can eliminate several terms of the governing equation since they are insignificantly smaller than both the current of the electrons and ions. Resolving the equation yields us a voltage which can be solved through an iterative process using the electron temperature. Solving iteratively gives us a voltage of negative 2000, which is sufficiently high enough to cause electrostatic discharge.
Here are our references for our presentation today, and here's the code that was developed for it. Thank you. Have a good day.